Okay, let's talk about probability. And I know, that word can sometimes sound a little intimidating, right? Like we're about to dive into some super complex math homework. But stick with me here, because that's not what this is about. I want you to think of this differently. We're going to be building a practical, really powerful toolkit, a toolkit that's going to help you make sense of all the uncertainty that's just part of life. So, a fair question to ask right up front is, what are the odds we can actually make sense of all of this in just a few minutes? Well, I'm going to go out on a limb and say the probability is very, very high. I mean, we're talking close to one for sure. We're going to take a really clear and structured journey through the essentials. And by the end, you're going to walk away with a whole new set of mental tools. Okay, so here's our blueprint. This is how we're going to build that toolkit, piece by piece. We'll start with the basic lingo, grab some essential rules, figure out how to organize everything, see it in action, and then we'll finish with a real power tool for updating our thinking when we get new info. You ready? Let's get to it. All right. First things first, before we can start using any of these awesome new tools, we've got to learn the lingo, right? This is the foundational vocabulary. We'll need to talk about chance. So let's start with the big one, probability itself. What is it really? Well, at its core, it's just a number. A number that's always, and I mean always, between 0 and 1. It's simply a way to measure how likely something is to happen. If the probability is 0, it's totally impossible. Think rolling a 7 on a normal 6-sided die. If it's 1, it's a dead certainty. And of course, most things in life falls somewhere in between. Next up is the word experiment. Now, in probability, this doesn't necessarily mean test tubes and lab coats. It's just any process that gives you a result. It could be something as simple as rolling a die, or something more complex like randomly selecting two families from an entire town. Okay, this next one is super important, the sample space. I love this idea. You can think of it as a complete map of every single possible thing that could happen in your experiment. So if we're back to rolling that die, the sample space is simply the set of all the outcomes. 1, 2, 3, 4, 5, and 6. That's it, the whole shebang. And our last piece of lingo for now is mutually exclusive events. It sounds kind of formal, but the idea is really simple. It just means two things that absolutely cannot happen at the same time. You flip a coin once, right? It can land on heads or it can land on tails. It can't land on both. Getting a head and getting a tail on that one flip are mutually exclusive. Okay, we've got the vocabulary down, we're speaking the language of chance. Now it's time to actually open up that toolkit and grab our first, most essential tools. These are the basic rules that are going to let us start doing some calculations. So this is our first formula, the general law of addition. Now, don't let the symbols throw you off. Let's break it down. This is what we use when we want to find the probability of one thing, let's call it X, or another thing, Y, happening. That U-looking symbol, that's called a union, and you can just think of it as the word or. So the rule says we take the probability of X, add the probability of Y, but then, and this is crucial, we have to subtract the probability of X and Y happening together. We'll see why in just a second. Okay, let's make this real. Imagine a company surveyed its employees asking, what would make you more productive? And the two big options were noise reduction or more storage space. This table shows us exactly what they said. You can see right away that 70% of people wanted noise reduction, and 67% wanted more storage space. And of course, you can bet some people wanted both. So let's apply our new rule. We want to figure out the probability that if you picked an employee at random, they wanted noise reduction or more storage. So we take the probability of someone wanting noise reduction, which is 0.70, and we add the probability of them wanting storage, which is 0.67. Now, here's where that last part of the formula comes in. If we just add those two together, we've actually double counted the people who wanted both things. See that 0.56 in the table? Those people were included in the 70% and in the 67%. So we have to subtract that overlap, that 0.56, to get the correct answer. It's all about avoiding double counting. See how useful that table was? Well, when things get a little more complicated, we have a special tool for the job. It's called a contingency table. And honestly, it's like a workbench for your data. It just lays everything out nice and neat so you can see all the relationships at a glance. Check this out. Here's a classic example with employee data. So the numbers on the inside of the table, like see the 31, that represents people who are both male and in a professional role. We call those joint frequencies. They show where two categories overlap. Then you have the numbers on the outside edges, in the total rows and columns. Those are called marginal frequencies. They just give you the total for one category. For instance, you can see there are 44 professionals in total, and 100 males in total. It just organizes the whole picture. Up to this point, we've been looking at probabilities from a wide open perspective. But what happens when we already know something? What if we have a little piece of extra information? This is where our next tool comes in. It's called conditional probability, and it's all about figuring out the odds of something happening given that something else is already true. And here's the formula for it. Now see that vertical line between the A and the B? You can just read that as the word given. So P of A by B is just a shorthand way of saying the probability of A happening given that B has already happened. And here's the best way to think about it. We're basically shrinking our universe. We're ignoring everything else in the sample space and focusing only on the world where B is true. Then, inside that smaller world, we're asking, okay, now what are the chances of A? Let's make this tangible. Picture yourself on a used car lot. The dealer tells you some stats. 70% of the cars here have air conditioning, 40% have a CD player, and 20% have both. So you walk up to a car, you look inside, and you see it has AC. The question we're asking now is not just, what are the odds this car has a CD player? No, it's more specific. It's, given what I now know, that this car has AC, what is the probability it also has a CD player? This is where our formula becomes so useful. To find the probability of a CD player, given AC, we take the probability of having both things, which we know is 0.20. That's the top of our fraction. Then we divide that by the probability of our given event, or new smaller universe, which is the probability of having AC. That's 0.70. So we do the math, 0.20 divided by 0.70, and we get our answer. It tells us that if you're looking at a car with AC, there's about a 28.6% chance that it also has a CD player. And this whole idea leads us straight to another key concept, the difference between dependent and independent events. Think about it. In our car example, did knowing the car had AC change the probability of it having a CD player? Yeah, absolutely. That makes them dependent events. The outcome of one affects the odds of the other. Now, if two events are independent, they have no effect on each other. Like flipping a coin and then rolling a die. The coin landing on heads doesn't change the probability of you rolling a 6. They are completely separate. Okay, it's time to pull out the ultimate power tool from our kit. This one is a real game changer. It's called Bayes' theorem, and it's basically a formal mathematical way to update our beliefs in the face of new evidence. It's how we get smarter. Yeah, I know, this formula can look a little scary, but trust me, what it does is incredibly cool and logical. At its heart, Bayes' theorem is a way to flip conditional probability on its head. It lets us take a probability that's easy to figure out, like what's the chance of seeing this evidence if my theory is true, and it flips it to answer the question we really care about. Okay, now that I've seen this evidence, what's the chance my theory is actually true? Let's look at a classic problem to see just how powerful this is. Imagine a company buys printer ribbons from two suppliers, Alamo and South Jersey. We know some things beforehand. Alamo makes 65% of all the ribbons, and 8% of theirs are defective. South Jersey makes the other 35%, but they have a higher defect rate of 12%. Okay, so that's what we know going in. Then one day you grab a ribbon and it's defective. That's our new evidence. The question is, who's the likely culprit? Is it Alamo or South Jersey? Okay, let's plug this into Bayes' theorem and solve the mystery. Step 1 is the numerator, the top of our fraction. We want to find the probability that a ribbon is both defective and from Alamo. So we multiply the chance it's from Alamo, 0.65, by the chance it's defective given it's from Alamo, which is 0.08. That gives us 0.052. Now for the denominator, the bottom part, we need the total probability of finding a defective ribbon, period. So we do the same calculation for South Jersey, 0.35 times 0.12, and we add that to Alamo's number. That gives us our total odds of a defect. Then we just divide the Alamo part by that total part, and that gives us our updated probability. And here's the answer. Isn't that fascinating? Even though South Jersey has a higher defect rate, it's actually more likely that the defective ribbon came from Alamo. The probability is over 55%. So why is that? It's because of what we knew beforehand, our prior belief. Alamo just produces so many more ribbons in total that even with a lower defect rate, they are still responsible for more of the total defective ribbons. This is the magic of Bayes' theorem. It perfectly blends our starting information with new evidence to give us a much smarter, more accurate view of the world. And this logic is used everywhere. I mean, in your email spam filter, in courtrooms, in medical diagnoses. It's huge. And there you have it. In just a few minutes, we've built a pretty amazing probability toolkit. We've learned the language of chance, we've got the addition rule, we know how to handle conditional probabilities, and we even have Bayes' theorem to update our beliefs. These are incredibly powerful ways to think about the world. So that leaves me with just one question for you. Now that you have these tools, what's the first piece of everyday uncertainty you're going to analyze?